Okay, so question 2, big question on transition elements. First of all, electron structures. They've given you the starting bit here, but make sure obviously in general that you can do the whole thing. And the key to that is using your periodic table to guide you. So, it will remind you that in the first period you've just got 2 elements because only 2 electrons can go in, 1s2. In the second period you've got 2s2, 2 elements there, and then 2p6. And as you fill those up we get the 6 elements here. And then when you've got to start filling it in from yourself, you can see that the same pattern occurs in the third period, so 3s2 and 3p6. And then in the fourth period, which is where it gets tricky, again your periodic table reminds you, we're back in the S block, so we've got 4s2, and then we've got 3d, and in general you just count across and say, well, how many elements across is it within the D block, and that will tell you how many D electrons. Remember, there are a couple of odd ones, chromium and copper, where you've got to be careful with that, but generally that's the way forward. If you are past the transition series and over back into the P block, you'll have got 3D10 and then 4P, however many it is. But in our case we are dealing with transition elements. If we just get rid of this, we can complete those and see that for an iron atom we've got, as we said, 3s2, 3p6, and that will be true for all fourth period elements. And then we've got 3d6 because iron is the 6th one across in the transition series, and don't forget the 4s2. People often write these two the other way round, 4s2, 3d6, because that's the order that the periodic table gives you for how the orbitals were filled up. If you write it that way round, that's perfectly fine, so long as you don't miss the fact that the d electrons are there. Now, when you come to Fe2+, you've got to be a bit careful, because the rule is that they always lose their 4s electrons first. Okay, there are good reasons for that, which has to do with the way the orbital energies change when you form positive ions, but you just best learn it as a rule. But once you take an electron configuration like that and you start forming positive ions, 4s comes out first. So if it's Fe2+, which is what we've got here, the only difference will be that we lose those 4s electrons. Everything else is still in place. So that's the answer for Fe2+. Okay, now we've got to give properties of Fe2+, which are typical of transition element ions. And you've basically got 2 properties here. The most obvious one, and this one that keeps coming up in all the transition element chemistry you learn, is that they're likely to be coloured. Okay, so in crystals or in aqueous solution, transition element ions tend to be coloured. Another possibility is that they may well have catalytic activity. Again, that's a characteristic property of transition element ions, that they often have catalytic activity. Another characteristic property which is often given for transition elements in general is variable oxidation state. But you've got to be careful with that here, because it's asked about this particular ion in this particular oxidation state. So you can't just say variable oxidation state, because its oxidation state is +2. What you could though say is that it can readily be converted into ions with different oxidation states, such as Fe3+, and that would also be acceptable as a general property. So remember, those are the things that make transition element ions special: colour, catalytic activity, ability to change oxidation states, and also complex ions, but it gave you that one in the question, so you couldn't have that in this case. Okay, now we've got some redox chemistry. Because of the variable oxidation state thing that characterises transition elements, there's a lot of redox chemistry that's linked to them. So in this case, what it asks you to do is to look at that equation and to spot what's oxidized and what's reduced using oxidation numbers. You can do that in 2 ways. You can go through and identify every oxidation state for every element and write them all down, and then look at the ones that change. Or you can just in your head, but obviously be careful doing this, but in your head or via a bit of scribbling, you can identify which is the element that's oxidized, which is the one that's reduced, and just spot the oxidation states for those. So let's go through it. So we've got FeSO4 first of all. We know that this is iron 2+, so we don't actually really need to work that out because it's told us in the question that the iron is +2 in that oxidation state, in that compound. Plus 7H2SO4 plus Na2Cr2O7. This compound is sodium dichromate, and the element whose oxidation state changes in here is going to be the chromium. Remember that sodium, oxygen, they always have the same oxidation states in compounds. Chromium is the transition element. It's the one that's likely to change. So look at that one first, and you can see what its oxidation state is. It's a bit more work this time. Sodium, remember, is always +1 in compounds. So because it's Na2, we've got 2 lots of +1. Oxygen is always -2 in compounds. So we've got 7 lots of -2. So we've got -14 plus 2 takes us to -12. And so these two chromiums between them must add up to +12, because remember, neutral compounds add up to 0 overall. So we've got -14 from the 7 oxygens, +2 from the 2 sodiums, takes us to -12. So the two chromiums must add up to +12, so 2 times +6. Now on the product side, we've got 3 Fe2SO4 So again, you can see the sulfate bit hasn't changed, but the iron has this time, because 3 lots of sulfate take you to 6-, so those 2 ions must each be 3+. So those are +3. Okay, so immediately you can see that's the one that's been oxidized, because the iron's gone from +2 to +3, and we figured that out from the change in the number of sulfates. Okay, the sulfate ion is -2, so the iron is +2 there. 3 lots of -2 takes you to -6, so the 2 ions must add up to +6. Hence you can say that each one is +3. The chromium, we've got Cr2SO4 and again that's easy because you can see it's the same pattern here. 3 sulfates take you to -6, so the 2 chromiums must be +6, so again those are also +3 in that product. And then we've got sodium sulfate and water, and those are not interesting. You know, we know the sulfate is still sulfate as it was at the beginning. Sodium doesn't change, and nor do hydrogen and oxygen, so there are 7 of those. So we've identified the things that change, and we've just got to work out what that means in terms of oxidation and reduction. So the iron goes from +2 to +3. In other words, the Fe2+ is oxidized to Fe3+ because it got more positive, so that's oxidation. The chromium has gone from +6 to +3, so it's got less positive, and therefore it was reduced. Okay, so it's the same kind of stuff you've done endlessly since AS, but obviously it was a much more complicated equation. But hopefully you could see that in the end it works out in the same kind of way. Okay, next little bit is about stability constants. So you have to learn the definition of the stability constant based on an equilibrium that you're given. So here we've got the hexaquo FeH2O6 2+ plus 6 ammonias in equilibrium with FeNH36 2+ and 6 waters. So the stability constant is essentially an equilibrium constant for that reaction, and you have to remember it goes that way around, so it's for the formation of this complex. And the definition is that the stability constant normally would be the stuff on the right hand side, but because that's water and the concentration of water is essentially constant in aqueous solution, we don't write that in our expression. We just say, well, that's a constant concentration, so we build it into our value of K stab. Same as you do with Kw when you're doing pH stuff, where again a water term, rather than deal with it, we just say, well, it's constant, so let's build it into the equilibrium constant. So we're not going to worry about that. So all that goes on the top is the concentration of this complex ion, FeNH3 6 2+. Now notice that we've had to put two lots of square brackets in there. One in the middle because the complex ion has square brackets within its formula, and then another one round the outside to mean the concentration. And it looks a bit awkward, but you must do that because otherwise it's not clear what you mean. So one set of square brackets to mean concentration, one because that's how you construct the formulae of complex ions. And we know from the mark scheme that if you didn't put the double square brackets in, you would have lost a mark. Okay, on the bottom line, it's the things on the left-hand side, and that's straightforward. It's exactly as you would expect it to be. So we've got FeH2O6 2+, and again, we need the double square bracket there. One for the complex ion, one to mean concentration, times the concentration of ammonia, and that will be to the power 6, because there are 6 of them in the expression. So that's what you get for your stability constant. And now we've got to think about hemoglobin as an example of an iron 2 complex. So first of all, you've got to explain how ligand substitutions allow hemoglobin to transport oxygen in the blood. So you don't need to know a lot of detail about hemoglobin, but what you do need to know is that it's a protein that contains Fe2+, so here's the protein around it, and in the absence of oxygen, that has a water molecule forming a coordinate bond to it. And what happens then is that when there's lots of oxygen around, we get a ligand substitution reaction, and the oxygen acts as a ligand in place of the water. Then the hemoglobin floats around the body. When it comes to an area where the oxygen concentration is low, the oxygen will float off again and be replaced once again by water. And that's essentially how it acts as a carrier. So what you need for the 2 marks are, first of all, that oxygen can bind to the hemoglobin, replacing water in a ligand substitution to begin with, and then elsewhere in the body where the oxygen concentration is lower, the oxygen will be released and be replaced once again by water. So it's just a reversible ligand substitution, oxygen for water, and then the reverse again. In the presence of carbon monoxide, this doesn't work properly. Less oxygen is transported in the blood, and we have to suggest why it is. Well, the answer is that carbon monoxide binds in place of oxygen at the same binding site, and crucially, it binds more strongly. It's able to form stronger dative covalent bonds than oxygen is. It says we've got to explain what that means in terms of stability constants. So if it binds more strongly, the stability constant will be bigger. Remember, the stability constant is bigger, the more stable the complex is. So what we're saying is that the stability constant for the hemoglobin carbon monoxide complex is larger than it would be for the hemoglobin oxygen complex. And that means that the carbon monoxide binds preferentially over oxygen, and so the oxygen can't get in there to get carried around, and the hemoglobin doesn't work properly. So the points you needed to make are that carbon monoxide binds more strongly than oxygen, not just instead of, but crucially more strongly than oxygen at the same position, and that's reflected in the fact that the stability constant for formation of the hemoglobin carbon monoxide complex is bigger than that for the hemoglobin oxygen complex. Okay, let's move along to the next bit. Cisplatin, we're being asked about now. First of all, we've got to explain why it's neutral. So let's have a look at that formula for cisplatin, so we can see why that is. So we've got platinum, Cl2, NH3, 2. Ammonia is a neutral molecule, so that's got no charge. But remember that Cl, when it appears in complexes, is actually Cl minus. It's chloride ions, not chlorine atoms, that act as ligands. So we've got 2 lots of Cl minus. So if there's no charge overall, that must mean that the platinum is in a 2 plus oxidation state. So the sum of the charges, 2 plus, 2 lots of 1 minus, adds up to 0. That's what that's getting at. Then we've got to draw diagrams of the 2 stereoisomers. Okay, so stereoisomers, remember, means either cis-trans or it means optical isomers. And in the case of a square planar complex, we're talking cis-trans. So what you've got are square planar complexes. So you just put platinum in the middle of a square with 4 dative covalent bonds coming in around it, like that. And if it's cis, it means that if you take 2 ligands that are the same as each other, like the 2 chloride ions, that they're going to be 90 degrees apart. So in that complex, the angle between that chloride ion and that chloride ion between their covalent bonds is 90 degrees. So this one is going to be the cis isomer. In the trans isomer, again, just put the 2 chlorides on first so you can see the relationship clearly. If one goes there, the angle between that bond and the bond to the other chlorine is this time going to be 180 degrees, and that's what makes it trans. Once you've got those sorted out, you can just put the other ligands on. So here come the 2 ammonias, and remember to put its square bracket round it like that, and the same with the ammonias here. Be careful with that one. Make sure that you write it as H3N rather than NH3, so that it's clear that it's the nitrogen that forms the bond. Okay, so those are your 2 isomers. We've got to describe the action of platin in the treatment of cancer patients. Doesn't need lots of detail. All you have to say is that it binds to DNA and thereby stops replication or stops cell division. Something like that is all you need to describe how it works. And the last part of this was a bit tricky because you had to remember some organic chemistry here, and that's an important pointer, that obviously organic chemistry is very peripheral to this exam, but it's not completely excluded from it. So it's asking you about this ligand 1,1-cyclobutane dicarboxylate. And it's a bit of a trend, it seems, in this new exams that they're quite keen on introducing new and unusual ligands. So you need to be ready for questions like this. So let's see what we think. Well, cyclobutane. Butane, remember, means 4 carbons. So cyclobutane will have 4 carbons in a ring. And then di means 2. And carboxylate, well, a carboxylic acid, remember, has COOH. So carboxylate is the ion you get from that when it loses H+. So dicarboxylate means that it will have 2 of those groups attached to the cyclobutane, and 1,1 means they're both attached to the same carbon, because if that's carbon 1 and it's got 1 COO minus attached, the other COO minus must also be attached to carbon 1. So that is what the negative ion looks like. Okay, so the thing to do there is not to panic. And if you go through it systematically like that, and remember just some very basic how to name organic things from last year, then even something quite strange that you've never seen anything quite like before falls into place. Now we've got to decide how that can act as a ligand in a square planar platinum complex. So let's draw it out again. We've got the platinum here, remember, with 4 bonds around it. And we know that it's still got 2 ammonias because it's told us that this thing is here instead of the chloride ions. So we can put the 2 ammonias over here. And on this side, we need to use this. Now it's obviously the carboxylate groups that can act as the ligands. And it's important to remember that lots of ligands actually use these. So it's worth just looking in general how that works. Carboxylate group you can draw like that. Okay, COO minus. And it's the O minus with, well, it actually has 3 lone pairs, but only one of them is going to act as a donor group. So it's that lone pair on the O- atom which is going to allow it to act as a ligand. So what we can do is put these CO O- groups on here, but remember that we don't put the negative charges into the diagram, because always in complex ions you add up the total charge and put it outside the bracket. So those 2 O- will add up together with the platinum 2+ and make it a neutral complex. Okay, so we've got those 2 carboxylate groups, and those are both attached to the cyclobutane ring. Let's get rid of this bit so we can draw on our cyclobutane ring like that. So you can see I've just taken this structure and connected the 2 COO- groups up to the platinum. But as always, you've got to be careful with the charges, that the charges on the ligands and the charges on the metal ion in the middle, instead of being shown individually, are all just added up together to make the final charge, which is shown up here outside the bracket. But in this case it's 0 because we've got 2+ on the platinum and then a minus there and a minus there. And that's the structure that you want. And that's the end of the question.